Hi everyone, welcome to our next video. This will be on the quadratic function. So quadratic function by definition looks like this. And these are just our familiar parabolas. So anything that looks like this is going to be described by some function that looks like this. Now this is not, like a lot of things in math, this is the definition, but not always the most useful form of the quadratic function. And I particularly like, which is the subject of this section of the book, this form of the quadratic formula, which is the vertex form. So let's talk about the vertex form and what it means. So first of all, there's a couple things you should know. One, the vertex form allows you to graph using translations. So graph any quadratic using translations. Let's notice that all it's basically made up is of a horizontal translation, a vertical stretch and compress, and a vertical translation. So if you know and understand the material from the section on vertical translation or on translations, then you should be able to draw any graph. And then there also might be a reflection here. A is allowed to be negative. So if A is negative, this could also have a reflection with it as well. So if you know about vertical reflections, vertical stretch and compress, horizontal shifts, and vertical shifts, you can graph any quadratic. So let's look at what the different parts of the quadratic form or the vertex form mean. So I'm going to rewrite it down here. So we'll have f of x equals a x minus h all squared plus k. So this is basically what it means. And this graph is going to be for when a is greater than 0. So I have some parabola here. And so this point here, which is the lowest point on the graph in terms of y, is called the vertex. And the vertex is always going to be equal to h comma k. So notice that this value right here and this value here will automatically tell you where the vertex is every time of the equation. But this h also has another meaning. If we look at the line h equals k, so let me draw this in a different color. It's not part of the graph. Oops, sorry. Let's see. So if we look at this line, x equals h, this is known as the axis of symmetry. And what the axis of symmetry does is cuts this function in half. This piece right here, if you draw it with the computer, it's going to be completely identical to this one. Just they're mirror images of each other. So even functions are reflections through the y-axis, and this axis of symmetry is just that this symmetric line being shifted left or right. And those are kind of the basic things you need to know about a parabola at this time. Let me see. Domains. So your domain is always going to be, for these types of functions, all real numbers, but then your range for this, for a, so remember this is only for a greater than 0. So this is everything that's going to be from k to infinity, because this point here is k, and notice that when we get below this line, we're never, no vertical or horizontal line is actually going to intersect the graph. So it's not until we get above k that we're actually going to start hitting the graph, and that's where our range is. And there's one other thing. When a is greater than 0, the vertex is a local minimum, but it's also a absolute, also known as a global minimum. And what absolute global minimum means is that it's just the lowest point on the graph, anywhere on the graph. So one of the applications we're going to use this fact in is in what's called optimization problems, where you want to either find the smallest value or the largest value. So that's what this graph tells you when a is greater than 0. So let's look at a less than 0, which almost everything is going to be identical. Now let me start writing and it'll let me pull up. There we go. So if a is less than 0, again we're going to have a parabola. Again, its vertex is going to be the highest point this time. Again, your vertex is going to be h comma k, and again you're going to get an axis of symmetry at x equals h. So what changes? So for one, the domain doesn't change. So that's going to be, again, negative affinity to affinity, but the range changes now. Because notice what happens is that if I draw any line, if I'm above, so this is at value k, if I draw any line above that, I miss the graph. So that's not going to be in the range. But if I draw any value for any value of y below k, I'm going to hit the range. I'm going to hit the graph. So our range is going to be from negative affinity to k. And then notice that the vertex is now the highest point on the graph. So I'm just cleaning this up so it's not visually chaotic. So now this is the highest point. So now this vertex is both a global or it's going to be a local max, but it's also a global or absolute maximum, because it is the highest point. And again, this will come up in one of the future videos entitled Optimization with Quadratic Functions. So these are the salient features of the quadratic. And notice that they're mostly the same whether a is greater than or equal to 0. There's just minor changes in the range and the interpretation of the vertex as a local max versus a local min. Everything else is pretty much the same in terms of what we're going to understand about algebra. So next video is going to be talking about how do we get from this form to that form. And I will see you then.